Hi everyone, welcome once more to this YouTube channel on physical chemistry. Today we're going to look at determination of reaction order, rate constant and rate law for my experimental data. So how can I determine reaction order, rate constant and rate law from an experimental data? If you are seeing this video for the first time or if you are not subscribed to the channel, kindly go to this channel's button or icon, the bell, close to the channel's name, Best Science Brand, and tap on it once and get subscribed to the channel. So, physical chemistry, we are looking at a continuation of our lectures on rate of reaction of chemical kinetics. So, the rate of a chemical reaction R has been verified to be dependent on the concentration of the reactants in the given reaction raised to their respective order of reaction. So from our previous videos, the rate of reaction depends on the concentration of reactants raised to their order of reactions. So rate varies directly as concentration of reactants. So let's look at this example. We have an example of a unimolecular reaction. So this is a unimolecular reaction. We have a R, the reactant, capital A is the reactant going to product. So it's going to be a unimolecular reaction if small a is 1. So rate becomes a proportion, it varies with concentration of A. So it's assumed that the particle, the mole A, small a is 1 for it to be unimolecular. If it's bimolecular, then small a is going to be 2. So introduce the rate constant K, and the exponent Q, which represent the order of reaction with respect to reactant A, will have R equal to, bring the constant K, equal to K multiplied by concentration of A raised power Q, where that Q is the order of reaction. So equation 1 represents the hypothetical rate law of a unimolecular reaction, where Q is the order, A in brackets represent the concentration of A, where K is the rate constant and R is the initial rate of reaction. So now let us consider a particular example of a bimolecular reaction. Let's look at the bimolecular reaction involve two different reactants, capital A and capital B, giving us product. Where A, small a and small b are the stoichiometric number of moles. So rate of reaction varies also at the concentration of each of the reactants. So R varies, big R varies at the concentration of A, big A, and also the same R varies at the concentration of big B, A and B being reactants. So putting them together, we can say rate, big R, varies at the concentration of A multiplied by that of B. So you see that is a bimolecular reaction. That's why the rate varies with the concentration of two different reactants. Bringing the rate constant, so into the rate constant K, and expressing and the exponential terms Q and R on the constant terms, we have R equal to K multiplied by the concentration of A raised power Q and the concentration of B raised power R, where Q and R are the order of reactions. Q is the order of reaction with respect to A, and R is the order of reaction with respect to B. We say the terms Q and R are the reaction order with respect to reactant A and B respectively. If I want to get overall order of reaction, I will add Q to R. Overall order now becomes Q plus R. So equation 3 is the hypothetical example. Experimental law, hypothetical experimental law for a bimolecular reaction. So equation 3 here you see represents a rate law for a bimolecular reaction, while equation 1 represents the rate law for a unimolecular reaction because it involves only one reactant particle, and then equation 3 involves two reactant particles. That is the bimolecular reaction involving two different substances. Now let's look at a hypothetical example of a thermomolecular reaction. Thermomolecular reactions are reactions that involve three different reacting particles. You see capital A, B, and capital C, that the reactants, where Y small a, B, and C are the number of moles in each reactant. As we say, the rate of reaction will depend on the concentration of each of the reactants. So you see that R varies directly as A, concentration of A, that of B, and that of C. Bringing them together, we'll now say R varies directly as the concentration of both A, B, and C together. We bring in the rate constant K, and then we have an equation of this nature. R equal to K, A raised to power Q, B raised to power R, and C raised to power Z, where Q is the order of reaction with respect to A, R, order relation respect to B, and Z, order respect to C. Overall order is obtained by adding Q, R, and Z all together. So equation 4, which we have explained, is the hypothetical rate law for a thermomolecular reaction. So when we are given experimental data, it is expected of us to obtain the order of reaction and the rate constant for the given set of data. So in this video, our interest is to learn how to obtain rate of reaction, order of reaction, and even rate constant when we are given experimental data. So look at the derivation of order of reaction of a unimolecular reaction. So let's look at the steps involved. Number 1, write the hypothetical rate law of the given reaction unless otherwise given. So you have to write the hypothetical rate law of the reaction given to you unless the rate law have been given to you in the question. Then number 2, consider any two sets of experiment and substitute the data in these sets into the hypothetical rate law to obtain equation 1 and 2. Step 3, divide equation 2 by 1 and solve to obtain the order of reaction. Then step 4, write the experimental rate law or equation by substituting the order of reaction obtained above into the hypothetical rate law. Step 5, substitute the value of the concentration of the reactants, the initial rate of reaction using any given set of experiment, and calculate the rate constant K. So let's look at the steps once more. The first step says write the hypothetical rate law of the given reaction unless it's given to you. Second step, consider any two sets of experiment and substitute the data in these sets into the hypothetical rate law to obtain equation 1 and 2. Divide equation 2 by 1 and solve to obtain the order of reaction. Write the experimental rate law or equation by substituting the order of reaction obtained above into the hypothetical rate law. Substitute the value of the concentration of the reactant in initial rate of reaction using any set of experiment and calculate the value of K. So let's look at an example. You ask example 1, derive the order of reaction, the rate law. Number 2, the rate constant for the decomposition of ethanol using the data below. So you have ethanol decomposing into methane and carbon 2 oxide. We're given experimental data, serial number 1, 2, 3, 4. The first column, initial concentration of ethanol in mole per liter, 0.10, 0.20, 0.30, 0.40. Initial rate in mole per liter per second, 0.020, 0.080, 0.180, 0.320. So how do we solve this? Look at the equation given to us, written again. Ethanol decomposing to methane and CO. First, we write the hypothetical equation for the reaction. That reaction is the unimolecular reaction because it involves only one reacting particle. So the rate of reaction will vary directly at the concentration of ethanol. So you see the expression R varies as the concentration of ethanol. Then we bring in the rate constant K equal to CH3, CHO in bracket, that concentration raised power Q, where the Q is what we're looking for, the order of reaction. Next, consider any two sets of experiment and substitute the data in these sets into the hypothetical rate law to obtain two equations 1 and 2. So we're going to look at go to the data, choose any two set convenient for you, and then substitute into this equation. So I would say we're going to choose from set 1 and 3. You can still choose 1 and 2 or 1 and 4. So substitute the data from set 1 into the hypothetical rate law. So from the set 1, our rate is 0.02. Our ethanol concentration is 0.10 from the table. So replace rate with 0.02, replace ethanol concentration with a 0.01 raised power Q. That is in this rate law, which we have quoted here. To replace rate with 0.02, replace concentration of ethanol with 0.10. Then you have power Q. Okay, the rate is already there, given to you, so you can see it up there. That are equal to K bracket CH3 CHO is power Q. So make your substitution We use that experimental data 1 to make that substitution. We now obtain equation 1. Then substitute the data from experiment 3, say 3 into the same rate law. The rate law is given as R equal to K, CH3, CHOQ. Our R is in set 3 is 0.180 mole per dnq per second. Our concentration is 0.30. We substitute again R from the rate law as 0.180 and substitute the value of the ethanol concentration as 0.3. This power Q becomes equation 2. We now divide equation 1 with equation 2. Or you can see divide equation 2 with equation 1. Anyone works out. So we have 0.180 all over 0.02. Find the two rates. 0.180 by 0.202. Then divide the K times, that is the other side, K is 0.30 power Q by K multiplied by 0.10 power Q. When divided to, you see that K cancels K. We divide the left hand side 0.180 by 0.02, we get 9. Divide the right hand side 0.30 by 0.1, you get 3 to the power Q. You only take one Q since both of them are raised power Q. Then when you have done that, using indices, 9 is 3 raised power 2. So you now simplify the left hand side, 9 is 3 raised power 2 equal to 3 raised power Q. They have the same base. 3 cancels out, so Q becomes equal to 2. So the reaction, we have gotten the order. The reaction is second order reaction. Number 2, we ask the order. So we have done it number 1. Then go to number 2, say reaction is second order reaction. The experimental rate law is obtained by substituting. Because number 2 says we should write the experimental rate law. So what do? We substitute the value of Q, which is 2, into the hypothetical rate law, which we quoted initially. Arrow K into CH3, CHO, bracket closes Q, place K with 2. So that R equal to K, CH3, CHO, bracket Q is a hypothetical rate law. So, but we now have the experimental, since we obtain the order, we place the Q with 2. We now have the experimental rate law. Number 3 says we should find the rate constant. In order to obtain the rate constant K, choose any of the experimental data, say example is set 1. You can use any set, doesn't matter, and substitute the given data into the experimental rate law derived above and calculate K. So from set 1, our R is 0.02 mole per dnq per second. Our ethanol concentration is 0.1 mole per liter. So we substitute. But first of all, since we're looking for K, we can make K the subject. So make K the subject from R equal to K, ethanol concentration raised power 2. Divide both sides by the ethanol concentration raised power 2, so that you can make K the subject of the formula. You now have K equal to R all over the concentration of ethanol raised power 2. You then substitute with the values in experiment 1. Use R 0.02 all over. Then the concentration of ethanol in state 1, experimental state 1 is 0.10 raised power 2. Then solve for your K. We solve for K 0.02 all over 0.01. 0.1 squared is 0.01. Then you have the unit also squared. Mole becomes mole squared. Per liter becomes per liter squared. On the denominator, you can see that. So you now have 2 per mole liter per second as the rate constant. So the unit of K should be derived accurately. How to get the unit of K? We divide the unit of the numerator by the unit of the denominator. So the unit of the rate constant K is derived by dividing the unit of the numerator with that of the denominator as in the above expression. So look at the numerator, mole per liter per second divided by mole squared, then liter squared. You see that if we take mole on the numerator, the exponent, the power is 1. We now collect the powers. Taking the 2, mole squared up, taking the 2 up becomes 1 minus 2 to apply indices. And then under the liter per liter minus 2, the power on liter goes up and becomes plus 2. Then second appears only once on the numerator. So we add up the powers. We now have 1 minus 2 give you minus 1 per mole, and then minus 2 plus 1 gives you 1, that liter, and then per second. So that's the unit of K, how we obtain the unit of K. Going over to example 2. Say in the following reactions, a cobalt chloride bond replaced by a cobalt water molecule bond. You see the reaction between that cobalt complex and water in the equation given to us. And we're given the initial rate as K into the cobalt complex raised power M. So using the data below, we ask find the value of M in the rate expression and calculate the value of K. If you look at this reaction, there are two reactants. So being that is water and the cobalt complex, which show that it's a bimolecular reaction. But in the rate equation given to us, only the cobalt complex represented. That is, water is not involved in a rate equation or in the hypothetical rate equation. You can observe it very well. So we have a table here. Initial concentration of a cobalt complex given to us 1.0 to the power minus 3. And then the initial rate 1.3 to the power minus 7. Number 2, initial concentration of a cobalt complex is 2.0 to the power minus 3. And its initial rate is 2.6 to the power minus 7. Then number 3, the third set 3.0 to the power minus 3 is the initial concentration. The initial rate is 3.9 to the power minus 7. Then the fourth 1.0 to the power minus 2 at the concentration. The rate is 1.3 to the power minus 6. So this is more like the first example, except that the difference here is that there are two reactant molecules by molecular reaction, but the rate only brought in only one of the reactants. So having done that, we go to the solution. We have the initial rate expression written down, the equation written above. We say we observe that though the reaction is a bimolecular reaction, but it is only the concentration of the metal complex that is represented in the habitable rate law. Water is not represented, hence we solve the exercise the same way as the first example. I explained that before. So first, consider any two sets of experiment and substitute the data into these sets. The data in these sets into the habitable rate law to obtain two equations, 1 and 2. So you choose any two sets of experiment. You can choose 1 and 2, you can choose 1 and 3, and so on. You substitute the value, okay, let's say substitute the data of the experiment from set 1. Let's choose set 1 now into the habitable rate law. So which is initial rate equal to K, then consider of the cobalt compressed power M. The rate for the first set is 1.3 power minus 7, and the consider of the cobalt compress is 1.0 to the power minus 3. You substitute into this that initial rate, replacing R with 1.3 to the power minus 7, replacing the cobalt compress with 1 to the power minus 3. We obtain equation 1 using set 1 data. We now say substitute the data from experimental set 2 into the same habitable rate law to obtain equation 2. We now choose the values from equation set 2 of the experiment and then make a substitution. From the set 2, rate is 2.6 power minus 7 mole per dm³ per second. The cobalt concentration is 2 times power minus 3. We bring the values, we have 2.6 power minus 7 equal to K times 2 times power minus 3. There is power M. So we make substitution using any of the two sets into a hypothetical rate law. That's what we did. You can use equation 1. You can choose any two sets of equation, doesn't matter. Then divide equation 2 with equation 1. This is equation 2. 2.6 power minus 7 is the rate. While in equation 1, the rate is 1.3 power minus 7. So we divide the rates together, we have that. We now divide their concentrations together, we have that. You see that 2 power minus on the right hand side, 10 power minus 3 cancel 10 power minus 3. And K also cancels K. So we are left with only 2 and 1 as a denominator, 2 up and 1 down. So we divide 2.6 power minus 7 by 1.3 power minus 7, you get 2. Then the right hand side will also give us 2 to the power M. K having cancelled each other, and then 2 power minus 3 having cancelled each other. We now have 2 equal to 2 power M. So cancel our basis. M is equal to 1. So the reaction is a first order reaction. And the rate law is then giving us rate equal to K, cobalt complex concentration raised power 1. There's nothing after the bracket. That means the power after the bracket should be 1 since the first order reaction. Number 2, we are out to find the rate constant. In order to obtain the rate constant K, choose any, just like the way we did the other one. choose any of the experimental set. Example, use set 1 and substitute the given data into the experimental rate law derived above and find your K. So we use set 1. Our rate is 1.3 power minus 7 mole per liter per second. Then our concentration of the cobalt compress is 1.0 power minus 3. We now go to our experimental rate law that we have derived. Replace R. Okay, we'll make R the subject first. You make K the subject first. Make K the subject by dividing both sides by the cobalt complex concentration. We now have K equal to R all over the cobalt complex concentration. So the rate from experiment data 1 is 1.3 power minus 7, and the cobalt complex concentration is 1.0 power minus 3. So you bring them into this expression and then divide all through to get the value of K. So K gives us 1.3 power minus 7 plus 3, applying indices. Because if you look at the numerator, the numerator is 3 power minus 7 and the denominator is 3 power minus 3. So you can just apply simple indices. The minus 3 going up becomes plus 3. We now have 1.3 power minus 7 plus 3, giving us 1.3 times power minus 4 per second. So you look at the unit, you see that mole has cancelled mole, per liter has cancelled the remaining per second. So unit of K in this case, or for first order reaction, is per second. We now move over to derivation of order of reaction of a bimolecular and thermolecular reaction. So what you have, because the first two examples we considered is derivation of an order of reaction of a unimolecular reaction. So, but this time around, we're talking about a bimolecular reaction. So what do? Number one, write the hypothetical rate law of the given reaction unless otherwise given to you. Just like in the first example, for a bimolecular reaction, consider any two states. So repeat step 2. For a bimolecular reaction, consider any two sets of experiments in which the concentration of one of the reactants is held constant. That is, concentrations are the same, while the second reactant has a varying concentration. If the reaction is thermolecular, that is, involves 3 reacting particles, then consider any two given sets of experiments in which the concentration of 2 of the reactants are held constant, while the third reactant has a varying concentration. So look at that when we go to examples. Then substitute the varying concentrations and their corresponding initial rate R into the hypothetical rate law to obtain equation 1 and 2. Then the fourth step, divide equation 2 with equation 1, determine the order of reaction. Then the fifth step, with calculated order, write the experimental rate law or equation. Then the sixth, substitute the value of the concentrations of reactants, initial rate of reaction R, using any set of experiment and calculate the rate constant. So let's go to an example and see how to carry out those steps. Example 1 says A plus B giving us product. We have a bimolecular reaction where A and B are different reactants. And the question says the data given below was generated for the above reaction at 25 degrees Celsius. You can see a table whereby we're giving the reactant A and B, their concentrations are given to you. You have the concentration of A from serial number 1 to 5, 0.01, 0.010, 0.020, 0.020, and then 0.010. You have the different or the corresponding concentration of B, 0.01, 0.02, 0.01, 0.02, and 0.02. You have their corresponding rates, 1.2 to the power minus 4, 2.4 times the power minus 4, 6.0 times the power minus 4, 4.8 to the power minus 4, and 4.8 again times the power minus 4. And we ask, from the above experimental data, determine the order of reaction with respect to each reactant, and then B, the overall order of reaction, C, the rate constant. So we'll go to the solution. The first one says find the order of reaction with respect to each reactant. For the solution, we have to write a hypothetical rate equation for the reaction, which is R equal to K, consist of A in square bracket raised to power Q and B raised to power R. Why do we use A and B? Because A and B, not only that they appeared in the as reactant, their concentrations are given on the table, A and B, unlike the previous example that was solved. So we'll now continue. Next, we'll move to the table and consider two sets of data where the concentration of the reactants is held constant while the other vary. The concentration of one of the reactants is, let's repeat it. Next, we move to the table and consider two sets of data where the concentration of one of the reactants is held constant while the other vary. So we'll go to the table and find out any two sets of data where the concentration of either A into the two sets are constant and B is different, or that of B is constant and A is different. So we'll look at, we'll say in experimental set 1 and 2, the concentration of A are constant while that of B vary. So let's go back to the table and see whether this is true. So we'll look at the table. Experimental serial number 1 and 2, concentration of A in serial 1 is 0.010 and in 2 is 0.010. So that means A is held constant, and concentration of B in the first set 1 is 0.010, and then in set 2 is 0.020. That means B is varying. So we're going to use experiment 1 and 2 whereby A is constant and B is varying. So we'll move back to where we were before. We'll now say substitute the concentration of B and the rate constant from experiment 1 into the hypothetical rate law, given as R equal to K, concentration of A raised to power Q and B raised to power R. So we substitute only B, the one that is varying, and ignore A. We substitute only the one that is varying, that is B, and ignore A. So B concentration is 0.010, and the rate of reaction for that step 1 is 1.2 to the power minus 4. So you can see it. B is 0.10 and the rate is 1.2 power minus 4. So we'll go and substitute these values into the hypothetical equation. Replace R with 1.2 power minus 4 and replace B with 0.010 raised to power R. A is removed or eliminated. We have equation 1. Again, substitute the concentration of B, reactant B, and the rate constant from experiment 2 into the applicable rate law to get equation 2. So we'll go to equation 2. Remember, we chose equation 1 and 2. Equation 2, and replace B concentration with 0.02 and the initial rate, which is which is 2 times power minus 4. Go to the table and see verify. In this experiment serial number 2, B is 0.020 and the rate is 2.4 power minus 4. Remember that A is held constant, so ignore A. So we'll continue. We'll now substitute the value of rate with 2.4 power minus 4, and then the B concentration at 0.020 to the power R. We ignore A. That's equation 2. We now divide equation 2 by equation 1. Equation 2 with equation 1, we divide 2.4 to power minus 4 by 1.2 power minus 4, as you can see there. We also divide K in equation 2, K, the right hand side, K bracket 0.020 raised to power R with K into 0.010 raised to power R. Now we see the right hand side. So K cancels K. If K cancels K, 2.4 to the power minus 4 divided by 1.2 power minus 4 gives us 2. While 0.02 in bracket divided by 0.01 gives us 2 also. But now raised to power R will take one of the R's. So that means equating basis. equating exponents, the base 2 to cancel each other, then R is equal to 1. That means reaction is first order with respect to B. So we have gotten R, and that R is an exponent on B. So our reaction is first order with respect to B. So we're going to find Q, which is supposed to be the order with respect to A. To find Q in experiment, we now go to experiment, the table again. We'll look at experiment say 2 and 4. We say in experimental say 2 and 4, the condition of reactant B are constant, while that of A varies. Substitute the condition of reactant A and the rate constant from experiment 2 into habitable rate law, which is R equal to K, A raised to the power Q, and B raised to the power R. So we pick experiment 2 first. Let's look at experiment 2 and 4 and see what we said is correct. Experiment 2 and 4. Let's look at experiment 2. Under A, concentration is 0.010. Then under B, 0.020. We go to experiment 4. Under A is 0.020. So A is varying. Experiment 2 for A is 0.01 concentration of A there, and then experiment 4 0.02. A is varying. Then B, experiment 2 0.020, and then experiment 4 0.020. So B is constant. So we can now ignore B and use A. So we go back to where we are. So continue to scroll to where we are. So we say substitute in experiment 2 and 4. The concentration of B are constant, while that of A vary. So substitute the concentration of reactant A and the rate constant for experiment 2 into the habitable rate law. We still go back to the habitable rate law. The concentration of A in experiment 2 is 0.010, and the value of R, corresponding value of R, is 2.4 to the power minus 4. We substitute. We now have R in place of 2.14 to the power minus 4 in place of R. Look at equation 1 there, and then replace A, concentration of A, with 0.010 raised power Q. B is ignored because the concentration of B is constant. Again, we substitute the concentration of A, reactant A, and the rate constant from experiment 4 into habitable rate law to get equation 2. So from equation 4, yes, from experimental set 4, our concentration of A is 0.020 and the rate is 4.8 power minus 4. We still do the same thing. Replace R with 4.8 power minus 4 and replace concentration of A with 0.20 raised power. I think there should be an error here. Raised power. A is raised power Q, not Q. Yeah, that is right in equation 1. And also we are substituting for A, so that should be raised power Q, not R. Let me make the correction. So the correction has been effected. So the K into 0.020 raised power Q, because we are working for A now, for Q, the concentration of A what we are using. So we divide equation 2 by 1. Equation 2, you can see it there, 4.8 raised to the power minus 4 divided by 2.4 raised to the power minus 4. We have it there. Then we'll divide the right hand side, which is K, into 0.020 raised to the power Q by K into 0.010 raised to the power Q. So when we solve that, 4.8 to the power minus 4 by 2.4 raised to the power minus 4, when you divide, you get 2. Then 0.02 divided by 0.10, you get also 2Q. So equal basis, we now take the exponent. Basis cancelling, we now say that Q is equal to 1. The reaction is also first order with respect to A. So number B says we should write the experimental law. The experimental law is therefore R equal to K into A, concentration of A, and multiplied by concentration of B. there's no power on A and there's no power on B, because the power on A, that is Q, have been found to be 1, and the power on B, that is R, have been obtained to be also equal to 1. So the reaction is first order with respect to A, and also first order with respect to B. So we have to find the overall order. Overall order is going to be R plus Q, 1 plus 1 giving us 2, second order reaction. Having obtained the overall order of reaction, we now go to question C, which say determine the rate constant of the reaction. So go to the solution. We make the rate constant the subject of the formula in the experimental rate law. So our experimental rate law R equal to K multiplied by concentration of A, then concentration of B. We recall that the concentration of A is raised power 1. That is, the ratio is first order respect to A and first order respect to B. So we'll make K the subject of the formula by dividing both sides by concentration of A and B. So K becomes R all over A concentration multiplied by B concentration. So to find the rate constant, then we use any of the experimental data. Example, experiment 1, to substitute the values of the concentrations and rate in the above formula. So use any of the data you have in the table to substitute the value of R, A, and B. And in this work, we chose experiment 1. You can use any set of experiment to evaluate K. So let's go to the table and see experiment 1 or experiment set 1. So this is the table. So in the experimental set 1, the concentration of A is 0.01 mole per dm cube. That of B also 0.01 mole per dm cube. And the rate of reaction is 1.2 times power minus 4 mole per liter per second. So you can use any set of experiments to evaluate K. So we choose experiment set 1 to evaluate our K. So we have from experiment 1, concentration of A is 0.010 as we saw in the table, B 0.010, and the rate of reaction 1.2 power minus 4. We now substitute in the equation for K, replacing R with the rate of reaction, which is 1.2 power minus 4, and the denominators A and B concentration with their values 0.01 and 0.01 each. So when we solve, we have our rate constant as 1.2 per mole liter per second. So how do we obtain the unit of K? The unit of K is obtained by dividing the unit of the numerator by that of the denominator. So we look at what we have there. The unit of K was obtained by dividing the unit of the numerator by the denominator in the above calculation. So the numerator is mole per liter per second, as you can see there, mole per liter per second. The denominator is, we have mole and mole in each concentration term of the denominator. So mole times mole gives you mole squared, as you can see. Or we just take the unit mole per liter and mole per liter as we have it under as the denominator. So you can see mole per liter multiplied by mole per liter. So you see that one of the moles cancel one mole, and then per liter cancels per liter. We are now left with per mole liter per second as our unit of concentration. So having seen this example number 3, so we now look at the table once more and then relate this example 3 to example 2. So you look at this example that we solved now. We saw that the reaction is the biomolecular reaction involving two reactant particles A and B, biomolecular reaction, and then in the table the concentration of A and B were given to us. So that is why we have to look for two sets of data where either the concentration of A is constant or that of B was held constant to evaluate our rate equation. So if we now go to experiment 2 and see why would the experiment 2 that we did a few minutes ago, is also a biomolecular reaction. But why don't you use this method whereby we had to choose a set of data where a pair of data whereby the concentration of any of the reactant is set constant and that one was varying. So let's see why it was so. Why this one is different from the first one that we did. So for better understanding, we'll go through example 2 again and see in the following reaction of a cobalt chloride bond. In the following reaction, a cobalt chloride bond is replaced by a cobalt water bond. You can see the equation of the cobalt ammonia chloride complex right with water to give us the product cobalt ammonia and water complex, and then chloride ion formed. And then look at the initial rate expression given to us as R equal to constant K multiplied by the cobalt complex concentration raised to power M after the bracket. Now, if you look at this reaction given to us, the reaction involves two reacting particles, the cobalt complex and water. It's a bimolecular reaction. But you look at the rate constant, unlike the example 3 that we just saw a few minutes ago. In the rate equation or the habitable rate equation, only the cobalt complex was represented. Water was not represented. So water did not contribute to the rate of reaction. So that is why in this calculation we did not involve water, because the table will not give you the water concentrations. So the table or the experimental table gave the concentration of only cobalt complex, while water was not involved. But in the previous one we had A and B. Both A and B, their concentrations were given to us in the table. So let's look at the table once more. Look at the table. You see that we are given the concentration of cobalt complex and the initial rate of reaction, while the concentration of water was not provided in the table. So you see, water wasn't provided. So that is why we did not talk about water concentration. So all we have to do here is to consider any two sets of data, any two experimental sets, either 1 and 2, 1 and 3, 2 and 3, 2 and 4, 1 and 4, choose any two and divide their rates and also divide their concentrations. Like as we solve, just solving it as if we are dealing with a unimolecular reaction, even though this is bimolecular. It's a bimolecular reaction, but in actual sense, in the rate expression, only one subterm was represented. So we'll solve it as if we are solving a unimolecular reaction. So look at the solution once more. We have the equation, we have the initial rate given as K, then cobalt complex concentration raised to power M. So we observe that though the reaction is a bimolecular reaction, but it is only the concentration of the metal complex that is represented in the hypothetical rate law. Water is not represented. Hence, we solve this exercise the same way as the first example. The first example we're talking about here is the one that involves unimolecular reaction. So we say first consider any two sets of experiments and substitute the data in this sets into a hypothetical rate law to obtain two equations, 1 and 2. So here we're not keeping anything constant because we only have one substance in the experimental table. So we choose any two data of our own convenience. For example, experiment 1 and 2. So we say substitute the data from experiment set 1 into hypothetical rate law to obtain equation 1. The rate law given as K, cobalt complex raised to power M. So from experiment set 1, you can go to the table and look at set 1. So you can see the experimental set 1, the concentration of the cobalt complex is 1.0, that's power minus 3, while the rate of reaction is 1.3, the power minus 7. So go back to the solution. So as you can see there, the rate of reaction is 1.3 to the power minus 7, and the cobalt complex concentration is 1.0 to the power minus 3 mole per liter. So we substitute into replace rate or initial rate with 1.3 to the power minus 7, replace the cobalt complex concentration with 1.0 to the power minus 3. So to the power M, and that gives us equation 1. Repeat the same thing for using experimental set 2. So experimental set 2, the rate, let's go to the table and find out. So from the table, the concentration of the cobalt complex in the experimental set 2 is 2.0 to the power minus 3, while the rate is 2.6 to the power minus 7. So we have there, substitute the data from implementer set 2 into the hypothetical rate law to obtain equation 2. You see the hypothetical rate law, initial rate equal to K multiplied by cobalt complex raised to power M. Initial rate is 2.6 power minus 7, and then the cobalt concentration is 2.0 power minus 3. So we substitute the values, replace R with the rate, which is 2.6 power minus 7, and replace the cobalt concentration with 2.0 power minus 3. We will have equation 2. We now divide equation 2 by equation 1. So you see that connecting them together, 10 power minus 7 cancels 2 power minus 7 on the left hand side. 2.6 divided by 1.3 gives you 2, and then 10 power minus 3 cancels power minus 3 on the right hand side of the equation. 2 divided by 1 gives us 2. We now have 2 raised to power m, and also K cancels m. So m becomes 1, being the first order reaction. So we don't need to look for any other order, because that reaction will have only one substance in the hypothetical rate law. So you can see the difference between this example we just reviewed now, involving the biomolecular reaction, but whereby only one of the reactants was used or was seen in the initial rate law, and then that reactant is what was given to us in the table. Water was not provided. We solve it in the same way we solve unimolecular reaction experimental data. So we'll now go over to example 4. So this example 4 is talking about a reaction that involves 3 reacting particles. That is a thermomolecular reaction. So you say that experimental data for the following reaction at 25 degrees Celsius is given below. A plus B plus C giving us product. So you can see that the reaction is a thermomolecular reaction because it involves 3 reacting particles, one of A, one of B, and one of C. So we have the table for the experimental reaction generated from the experiment between A, B, and C. Serial numbers 1, 2, 3, 4. Consist of A reads 0.250, 0.250, 0.250, and 0.500. Then consist of B 0.250, 0.250, 0.500, 0.500, and then that of C 0.250, 0.750, 0.250, and then 0.250. Going to the rates of reaction. So for the first row, 4.00 to the power minus 5. Second row, 1.20 to the power minus 4. Third row, 1.00 to the power minus 4. And then the fourth row, the same 1.00 to the power minus 4. The question says, derive the order of reaction with respect to each reactant, and B, derive the rate law. We go to the solution. We see the reaction written again, A plus B plus C equal to product. We read the reaction involves 3 reacting particles. Hence, it is a thermomolecular reaction. In addition, the concept of the 3 reactants are all provided in the experimental table. So if you compare to example 2, or the example 4, the 3 of them were provided, and the example 3 also, the 2 of them, A and B, were also provided. So let's continue. In addition, the concept of the 3 reactants are all provided in the experimental table. Hence, we will write a hypothetical rate. Is that an error? We'll write a hypothetical rate. Rate equation involving all the reactants, since none was provided in the equation. So what we're saying that we look at the equation, the hypothetical rate equation was not given to us. So we're going to formulate one. So how to write it? We know that the rate of reaction or initial rate of reaction varies directly at the constitution of each of the reactants. So you see the expression initial rate equal to the rate constant multiplied by the constant of A, constant of B, and then constant of C. And we'll now add some exponents. So on A we have exponent Q, and then on R exponent R, on B exponent R, and on C exponent M. Those exponents are the order of reaction respect to A, B, and C. So small q, letter Q, is the order of reaction respect to A. Small r, the order of reaction respect to B, and then small m, the order of reaction respect to C. So having done that, next we'll consider any two given set of experiments in which the constant of two of the reactants are held constant. So since we have three reactants here, we have to look out for any two given set experiment in which two of the reactants have constant concentration, that is unchanging concentration, while the third reactant has a varying concentration. So to eliminate A and B, to eliminate reactant A and B in the habitable rate law given above, we will find any two sets of experiments in which the concentration of A and B are held constant. So we'll go back to the table and find any two set of experiments whereby the concentration of A and B are held constant. If you look at the table, look at experimental set 1 and 2. You observe that the concentration of A in experimental set 1 under the first row under A is 0.250. Then go to set 2. A is also 0.250. That means A is held constant in 1 and 2. Then go to B. You also observe that the concentration of B in the first row is 0.250. Second set is also 0.250. That means all in 1 and 2, B is also held constant. When you go to C, you observe that the concentration of C in the first set or first row is 0.250, and then on second set or second row is 0.750. So you see that C is not held constant. So we can now use 1 and 2 to eliminate A and B, because in the experiment 1 and 2, A and B have equal concentrations. Then observe their rate, the rate of reaction in 1, 4.00 to the power minus 5, and in 2, 1.20 to the power minus 4. We'll go back to the solution. We now say experimental set 1 and 2 have concentration of A and B held constant. So as we are seeing, substitute the varying concentrations C for experiment set 1 and 2 values and their corresponding initial rate into the habitable rate law. So since A and B are constant, we ignore A and B and only use C. So from set 1, the concentration of C is 0.250 mole per liter. Our initial rate is 4.0 power minus 5 mole per liter per second. And then we have the habitable rate law, initial rate equal to R equal to K, concentration of A raised power Q, B raised power R, and C raised power M. So we ignore A and B and make do with C. So the rate in experimental set 1 is 4.0 power minus 5 equal to K. The C concentration is 0.250. So we substitute there, replacing rate with 4.0 to the power minus 5, replacing C concentration with 0.250, and of course the order on respect to C is M. You see M there. That becomes equation number 1. We say note that the concentration of A and B we are not substituted in the above equation because they are held constant. So for experimental set 2, the concentration of C is 0.75 mole per liter, and the initial rate is 1.2 power minus 4 mole per liter per second. And we'll have the habitable rate equation. Before we continue on the substitution, or before we substitute the rate equation, we have to go back to the table and find out where we're going to use C. That means if I say 2, A and B are also held constant. So verify from the table as well. We'll now look at the experimental data 2. We still see that A is constant 0.250, B is constant 0.250, while C is different 0.750. That, and the rate is 1.2 power minus 4. So we still substitute with equation 2. We substitute for C and we ignore A and B because A and B are constant. So for experimental say 2, C is 0.75 mole per liter. The initial rate is 1.2 to the power minus 4 mole per liter per second. So initial rate is 1.2 to the power minus 4 equal to substitution now. K, they replace control of C with 0.75, which is given to you already from the table. And then ignore A and B because they are equal, they are constant. Raised power M, that equation 2. We'll now divide equation 2 by equation 1. Look at equation 2 there, the numerator, and look at equation 1, which now serves as the denominator. So we'll divide it to 1.2 power minus 4 divided by 4 times power minus 5 gives us 3. 0.75 divided by 0.25 also gives us 3. K cancels K. We'll now take M. So cancel out the bases that are equal. That means M is equal to 1. So reaction is first order with respect to reactant C. Now we obtain M, which is the order of reaction with respect to what does M represent? M, let's go back to the habitable rate law. M is the order of reaction with respect to C. Okay. So having done that, we continue to eliminate A and C in the habitable rate law given above. We find any two sets of experiment in which the constraint of A and B are held constant. We'll go back to the table and check. Experiments 1 and 3 have constraint of A and C held constant. So let's see how true that this is. Look at experiment 1. Experiment 1 has A 0.25 concentration, B 0.25 and C 0.25. Experiment 3 has constraint of A 0.25, B 0.50 and C 0.25. You look at 1 and 3, you see that constraint of A and C are the same in both 1 and 3, while that of B is different. So we eliminate the constraint of A and C in the rate equation by using equation 1 and 3. Okay, so we are there now. So we say substitute the varying constraint of B from experiment 1, set 1, and set 3 values and the corresponding initial rate into the habitable rate law. So the rate law is K conc of A raised power Q, B raised power R, C raised power M. So for experiment 1, B is 0.25 mole per dm cube or mole per liter. The initial rate is 4 times power minus 5 mole per liter per second. So replace rate as 4 times power minus 5, and then K, the constraint of B is what substitute now since A and C are constant. So replace constraint of B with 0.250 raised power 3. So note the constraint of A and C are not substituted in the above reaction because they are held constant. So we only make do with B. Then for experiment say 3, B is 0.50 mole per liter. Initial rate is 1.0 power minus 4 per liter per second. We also substitute from the experiment 3, substitute that of B and the rate. The rate is 1.0 power minus 4, and then the constraint of B is 0.50, there is power R. We ignore A and C as well because they are constant. We obtain equation 2. We now divide equation 2 by equation 1. You have equation 2 at the numerator. They are 1.0 power minus 4 equal to K raised power 0. K bracket 0.5 raised power R, and the equation 1 is 4 times power minus 5 equal to K bracket 0.25 raised power R. If you divide the two expressions or equations, for 1.0 times power minus 4 all over 4 times power minus 5 will give us 2.5, and then 0.5 divided by 0.025 gives us 2 raised power R. So we cannot simplify it by ordinary logarithm. What we'll do, we take log. By ordinary indices, we take log on both sides. Log 2.5 equal to r log 2, applying mathematics principles. So log 2.5 is 0.3979, log 2 is 0.3010. So divide both sides by 0.3010 to find r. So r becomes 0.3979 all over 0.3010, and that gives us 1.32. So the reaction is a fractional order reaction with respect to B, because the order with respect to B, that is R, is not a whole number. So we'll say it's a fractional order with respect to B. So to now eliminate B and C in the hypothetical rate law above, we find any two set of experiments in which the constant of B and C are held constant. We go back to the table and check again. Look at experiment 3. We see that constant of A is 0.250, B 0.500, and C 0.250. So experiment 3, A and C have equal concentration. Then go to experiment 4. You see that A is 0.500, B 0.500, and also C 0.250. So we see that in the fourth equation that B and C have the same concentration. So let's take an general overview. In experiment 3, A and C have the same concentration. So in experiment 3, I will see that B and C have the same concentration. In experiment 3, the concentration of B is constant in experiment 3, the concentration of B is constant in say 3 and 4, 0.50 and 0.50. And then concentration of C is constant also in experiment 3 and 4, 0.250 and 0.250. But concentration of A varied, 0.25 and 0.50. So we're going to eliminate B and C because using equation 3 and 4, because their concentrations are held constant while that of A varying, so that we can get the order of rest with respect to A. So we'll go back to where we are. So here we are. Substitute the varying concentration of A from experiment 3 and 4 values and their corresponding initial rates R into the hypothetical rate law. And the rate law is given as R, K, A raised power Q, B raised power R, and C raised power M. So we use experimental say 3. The A concentration is 0.25 mole per liter. The initial rate is 1.0 10 power minus 4. First, this is the value for experiment 3. We substitute it into that initial rate hypothetical equation, replacing rate with 1.0 power minus 4, and then replace the concentration of A with 0.25 raised power Q. B and C were not used because they had constant concentrations in equation 3. So we ignore B and C. So note the concentration of B and C we are not substituting in the above equation because they are held constant. Then for experiment state 4, A, concentration of A is 0.50 mole per liter. Initial rate is 1.0 10 power minus 4 per mole per liter per second. We'll now make a substitution again. Replace rate with 1.0 power minus 4, and the concentration of A is 0.50 raised power Q. B and R were ignored because they also had constant in experiment 4. So having obtained equation 1 and 2, we divide equation 2 by 1 as we used to do. So equation 2 is 1.0 power minus 4 equal to K, 0.5 raised power Q on the numerator, and the equation 1 is 1.0 power minus 4 K into 0.25 raised power Q as the denominator. Look at the expression. So 1.0 power minus 4 cancels out 1.0 raised power minus 4, and then on the other side K cancels K. So when we solve that, we divide 0.50 by 0.25. You have Q. So we now have 1 equal to 2 raised power Q, and then Q would be 0 because the number that 2 will be raised to power will be raised to give us 1 must be 0. Remember that any number raised to power 0 is 1. So Q is 0. That means reaction is 0 order respect to reactant A. B says we are asked to write the experimental rate equation. What we will now do, we substitute the Q, R, N with their actual values. We go to the the hypothetical rate equation that we had before. We now replace the constant of A. That Q was obtained as 0, so replace Q with 0. Replace B with what got as R. The value of the constant of the order with respect to A is Q. That is 0. We got that 0. The order with respect to B, R, we got as 1.32. And the other with respect to C, we got it as 1. And now, since A raised power 0 and any time raised power 0 means 1, so initial rate now becomes K, constant of B raised power 1.32 and C raised power 1. So A did not appear at the final initial rate of reaction because A, the constant of A raised power 0, the order of A is 0 order reaction, so that means A will vanish. So that bring the lecture to an end. So thank you for listening. If you have not subscribed to the channel, kindly press on the subscription button or subscription bell and get subscribed to the channel. Share our videos on social media, share our videos on Facebook, invite friends who are in science or engineering courses, or who are offering their postgraduate courses in chemistry or chemistry related courses, biochemistry and engineering, chemical engineering and chemistry courses. So thank you for listening. Thank you very much.